Good afternoon, all of you. Welcome to the last talk of the show. Delighted to all of you to be here. We are super excited to be here. My name is Jules Damji, and I'm joined by my colleague, Anthony Baum. And we're going to share with you how you can actually do fine-tuning and scaling your Hugging Face large language models with Ray AI. So super excited to be here. This is my, 14th or 15th summit that I've been presenting at. So I'm really decided to be among practitioners and the community over here. So thank you for coming. Now, before we introduce ourselves and who do we work for and what do we do, I just want to get a quick poll of how many of have you used or heard of Ray? Okay, you can stay. How many of you are using Ray today? Okay, brilliant, you can stay. Now I'm going to ask you a tongue-in-cheek question. How many of you have heard about Hugging Face? It's like asking, have you heard about Uber and have you ever used it? You know? Well, thanks a lot. You're at the right place and with the right presentation. So a little bit about myself. I am the lead developer advocate at Anyscale, part of the Ray team. Prior to that, I was at Databricks for about 6 years and at Hortonworks, where I led the same kind of efforts. And a long time ago, held many engineering positions at some of these notable companies who really, I was there at the right time, at the right moment to sort of see the evolution of all this different explosion that these companies were at the forefront. So I was very fortunate. And I have Anthony who will introduce himself.
Yeah, hey guys. So my name is Anthony. I'm a software engineer at Anyscale. I'm working on the libraries team, which is a part of our open source organization. And I'm mainly involved with Ray AI Runtime, so Ray AI, and specifically Ray Train and Ray Tune. And aside from that, I have been contributing to various other open source projects over the years.
So delighted to have him as part of my co-pilot. So who do we work for? We work for a company called Anyscale, who were the original creators of Ray. And Ray is this general purpose framework that allows you to scale your machine learning workloads or your AI workloads or your LLM workloads or your any Python applications at a massive scale. The important thing is that the general purpose framework that gives you some primitive abstractions for you to be able to write these distributed applications at scale. And what do we do? Anyscale is a managed service. Gives you the scalable compute, so you can actually, you as a developer can not worry about managing the infrastructure. It's a managed service for Ray. And why did we do it? I think why did we do it? You've been at this particular conference, you've heard about data, you probably heard about scaling. And scaling is a necessity today, right? It's no longer an exception, it is a norm. And scaling is hard. There are a lot of challenges associated with scaling. And our mission, our North Star really at Anyscale and with Ray right from the very get-go was to make sure that distributed computing is easy for any Python developer. You don't have to have a PhD in distributed computing. You don't have to be a machine learning researcher, but you should be able to, using Ray and doing LLM, or even distributed computing should be a lot easier. So here's the agenda today. We're going to talk about state of the AI and ML today. What I'm going to say today is probably obsolete already. The slides were done about a week ago, but the pace at which we are going is just amazing. And how we're going to make a case at how Hugging Face is at the forefront of the open source and making cutting-edge ML accessible to all of us in a very democratic way. I hate the verb democratizing, but we have to use it. Essentially, how easy it is for the developer to actually use that. But the first two things are impossible to do without distributed training as a necessity. And that's why I'm going to make a case that distributed training is a necessity, is not a norm. It is a norm, it's not an exception. And then we'll look at a few code examples to say how the Hugging Face transformers, along with integration of Ray AI, makes distributed computing easier. You just write Python code and it actually does all the underneath along with Ray. And then Anthony is going to deep dive into some of the Ray AI integrations we have done. In particular, when you actually want to fine-tune an LLM model using the deep speed libraries that Microsoft has provided, allows you to shard the models across very efficiently, so you don't have to write all the boiler code. And using the accelerators, and you don't have to worry about shifting your weights from CPU to GPU. And they will try to do a live demo. Network, hopefully, is in our favor. Nobody is using it, so hopefully be able to give you a live demo. We're actually going to train a model or fine-tune a particular model from Hugging Face. So what's the state of the AI today? I mean, I looked at this particular diagram, and you can actually see all these bubbles. And all these bubbles are really foundational to the model, which were just about a year ago. And these are large language models, which were sort of released, both open source as well as proprietary. And then just within a year, right, within a year, we've seen this explosion. Now, I don't know if I could attribute that to the Cambrian explosion, but there has been a phenomenal pace at which all these models are coming. Every day there's something. There's not a day that goes by without there's a tweet out there. There's not a day goes by with somebody that we raised an LLM model with all different sizes. So the pace at which all these models are being developed is phenomenal. And these are deep learning neural networks which are based on transformer models. Now, how many of you actually have read the seminal paper by Aswani in 2017 called "Attention is All You Need"? Right? And these transformer models are based on these neural architecture where you have encoders and decoders, and you have this attention heads, which are really neural networks that allows you to somehow predict what the next word is. And because they are based on this context window, which is larger, they can actually look back into what the context for the next word and give you the most probabilistic one. But I'm not going to go into what the architecture look like because it's something that is beyond the scope of this presentation, but you should actually read that paper if you really want to get an understanding of what's happening behind the scene when you actually issue a prompt and what happens. It's a beautiful paper. But these models somehow have released and unleashed some of the emerging capabilities in generative AI, right? And we have this explosion of all these LLM-based applications that you heard about today, you heard about yesterday, the day before, what you can actually do with these NLP tasks or natural language understanding. And you can write all these applications, and you can use these language models, which are either fine-tuned to a particular specific task, or you can just use the general model to do the general thing. And then they range from text classification to sentiment analysis, from determining a toxicity of a particular content that you might actually give it as a prompt, to entity recognition, where you can actually extract information out of a particular prompt or out of that, and language translation, huge. Today we heard a talk about PAM2, how PAM2 is so much better, even though the size is smaller, how they actually do transformation from one language to the other. Or you can do sentence completion, summarization. These are some of the tasks which are actually happening, or the Q&A and stuff. So these is something at the forefront. Now, how does Hugging Face transformers actually make it a lot easier for us? How does it make it easy for people to do that? Well, they're given us these Python program libraries, which are very opinionated, but they are very high-level abstraction that hides away all the complexities of the neural networks that you don't have to worry about how the transformer work. It does everything for you. It's mostly focused on some of the NLP tasks that you will be doing, machine translation, sentence completion, toxicity, all these things that I listed earlier, that these generation models have unleashed some of the capabilities that you can actually do. And they're based on this multiple trained models, both GPT, which is only a decoder, it's a causal model, or BERT, which is both encoders and decoders. And Hugging Face actually has a huge community, right? Their focus right from the very get-go was to make sure that everybody can actually have access to these open source models, which are pre-trained, and all you need is a checkpoint string, and you can actually download this particular model. They have Hugging Face spaces that other people have used applications that you can peruse to find out what they've done. They've got Hugging Face models where you can actually download this pre-trained weights and start using it directly with zero-shot learning, or you can actually fine-tune and train them. And they got associated data sets that you can actually use to further fine-tune it to your specific use case. So that's where sort of Hugging Face actually has done an incredible job. And how does it actually do it? Why is it so much easier, and why they have extracted away? The workflow is very simple. They got 3 stages, right? I can get a pre-trained model, and I can download it. Once I've downloaded the model, I have 2 choices. I can either fine-tune it to a specific use case with a data set that I want, or I can just use the pipeline inference API, which is a high-level abstraction where I can say, this is the task that I want to do, summarization, and here's my data set, here's my prompt, and then do the inference for me. So that's what the Hugging Face has given us, where it hides all the complexities that actually happen behind in a very simple workflow. And it increases developer velocity. If you actually wanted to just use any Hugging Face just to do pipeline inference, you can just do that in 3 or 4 lines of code. And this is huge because it is kind of popularized this notion that you can actually download any particular model and start using it in very simple workflow. And let me give you an example, right? Here is a simple code that 10 lines of code, and you can actually pretty much train your model on a new data set, right? This is from Hugging Face. So you import some of the classes, which are high-level classes, where you can specify, I want this to be an auto sequential classification, which is a BERT-based model, encoder and decoder. The training arguments, which is another class, which is the high-level abstraction. And the trainer that allows you to train things. And then I import my loads of data set. And then I load the data. So what I'm going to try to do over here is I'm going to classify a review from the Yelp. And I provide the checkpoint. And checkpoint is nothing but a string, right? A unique string that you can actually download it. I'm going to create an instance of the model from the particular pre-checkpoint. I'm going to divide my sets, my training data into training set. I create a training arguments, which is a class that's going to take that as an instance into the next set, which is a trainer. I give it the model that I've instantiated. I give my training data set. I provide the evaluation strategy that I want to use epoch, and I do trainer.train. And I'm done, right? Simple as that. But all that, as simple as it is, hides you all the complexity. But all that comes at a cost, right? The cost is that these models, when they are trained or when they are fine-tuned, require hardware resources such as GPU and CPU. And those have to be done at a particular scale. Now, today, we are blessed with what I call blessings of scale, right? Some of these models require exponential number of floating-point operations. You might be able to execute something on your laptop to about 10 billion instructions floating point per second, but these are exponential numbers, and you can only, nothing but you can actually have to scale out. That's why I call blessings of scale. But the blessings of scale is a two-way sword, right? It also introduces what I call compute supply demand problem, right? While you can actually scale, but you also have to worry about how you're going to satisfy to that. Now, Moore's law is dead. Everybody knows that, right? So we have all these hardware accelerators that come out from NVIDIA, that come out from all these different hardware companies who give us the GPUs and they give us the TPUs. Yet, there is a big gap, right? The big gap is we don't have enough compute power to be able to train a model from scratch. And our opinion is that the only way you can actually do this if you scale out in a very distributed manner, right? You really have to scale out horizontally. But when you do that, you introduce another new set of problems. And those problems are, now you got to worry about your developer velocity will decrease because you have to worry about managing a complex infrastructure, right? You have to make sure that you can manage this large infrastructures of hundreds and thousands of clusters and many CPUs across the entire cluster that you have. And that somehow has an effect on your developer velocity. You also have to be cognizant of the fact that you need to be able to use a framework that gives you the ability to work on different stages of an ML development. Whether it's a large language model, whether it's a large model that you're actually building, those are different stages, right? You have data ingestion, you have hyperparameter tuning, you have pre-processing, you have inference, and all that. So you need a framework that allows us to do that. And we contend that the solution for us and for all the developers out there to use what we call Ray AI, which is a Ray AI Runtime, which is built on top of Ray. And it has all these different components, all these different stages that allow you to do those things. You're going to do data ingest, and once you've done a data ingest, there might be a last mile ingestion that you actually want to do. You might want to do some transformation. You might want to do change of your images if you're doing image segmentation or image recognition. And then you want to feed those to your distributed trainer in a scalable manner. Once you've done that, once you've got the trained model, you might actually want to fine tune it, right? And then once you've tuned the model, you've got the right checkpoint, you won't be able to now do inference both online and batch inference at scale. And so what Ray AI Runtime gives you this scalable unified toolkit, which is built on top of Ray, that gives you the ability to do all these things not all at once, but individually. So if I just want to scale my workload for data ingestion and pre-processing, I can do that. I don't have to use the whole thing, right? It's not all or none. I can use individual pieces. I just might want to just do train. I already have my data sitting on a data lake or lake house. I can just get that particular data and I can feed it to my distributed trainer. Or I've already trained a particular model and I just want to use hyperparametric libraries that I want to tune in, and so on and so forth. So this is of a solution to be able to scale and increase the developer velocity. At the same time, you don't worry about the infrastructure management. Ray does that for you. And if you're running it on any scale, it does all the managed service for you. So here is sort of a high-level layered functionality of what I'm talking about, what Ray is all about. It can run on Ray can run on any of these cloud providers. Ray Runtime is built on top of Ray Core. And Ray Core actually has primitives such as tasks and actors. Tasks allow you to scale your function Python applications across the cluster. Actors are stateful services that allow you to do the same thing across the entire cluster. And then we have this thing called object store that you can actually share objects across the entire cluster. And these libraries, datasets, rlib, train, tune, and service are built using the Ray Core extraction. And out of the box, they have all this integration. So if you're using dataset to do data mile ingestion, you can use any of these data sources for that. If you're using training, you can use any of the deep learning frameworks that you're familiar with in Python that we integrate and then have specialized trainers for that. You can actually do that in a distributed manner, and you'll see one of those today. Or if you're doing hyperparameter tuning and you want to use external libraries, we provide both the algorithms to do your hyperparameter tuning and also the schedulers or the schedulers that come with it. So you can use our in-house one, or you can actually use one which are open source. And then if you actually want to serve, you can use any of those libraries. So that's sort of a layered cake of functionality that I give you. And here's an example of how you can actually use that, right? So if I want to read some data from data lakehouse, you can actually use the Ray data source to read your particular data. And once you've done the data, you can provide it to your trainer to train it. Once you train it, you can actually create a tuner and provide your trainer to do your hyperparameter tuning after you provided the scaling config. And once you're done that, once you actually get a checkpoint, you can predict. And when you get the results back, you can write it back to your data source. So I can use independently any of these different stages. So this is sort of an example. Now, if you're using JAX trainer, for example, to do your training against TPUs, you would actually be able to do that. Or if you're using PyTorch, if you're using Hugging Face trainer, you should be able to do that. So the question is, Jules, when would I use Ray Air? Why would I use it? Now, there are 4 scenarios where you actually want to use it. One is, as I alluded earlier, when you have a single workload that you want to do, you just want to do pre-processing and data ingestion. That's one case where you actually want to use it. That could be one of your workload. Or you actually want to build an entire end-to-end machine learning pipeline from scratch, from data ingestion, training, tuning, checkpointing, and serving. Or you actually want to use the existing ecosystem of Ray library integration, which is the case which we're going to show today. Or you actually want to use Ray as the foundational model on which you actually build your ML infrastructure. So Spotify has done that, Uber has done that, Instacart has done that, Sensora has done that, Shopify has done that. They've actually built the entire ML platform on top of Ray. So we extract it furthermore. So what we're going to talk about today is the third scenario where you actually use existing library that is combining Hugging Face with Ray Air, right? So here's a typical scenario, right? You want to use Hugging Face trainer to actually do some tuning. And you can take your existing Hugging Face code that you have done, which is your Hugging Face trainer arguments, your Hugging Face trainer that you actually use, and incorporate that or wrap it under a function called trainer.init per worker. And as the name suggests, this particular function is one that's going to run across all the workers that you have, along with a shard of the data that's going to train on, right? So you provide this particular, you wrap your Hugging Face code around it, and you just return that as a trainer. The next thing you're going to do is you're going to provide a scaling config. I want to use GPUs and I want 3 workers, or I want to use 100 workers, or however big your cluster is, you can actually do that. And finally, you're going to create a transformer trainer. This is the Hugging Face transformer integration that we have, which takes in the functions that you actually declare that's going to run across the entire cluster, along with the scaling config, so it knows that, and the data set that you actually want to do, that you want to train on, with evaluation and test, and you just call trainer.fit, right? As simple as that. And all the underlying complexity of how things get scheduled by the actor on all the machines is all underneath done by Ray. And now I'm going to switch over to Anthony, who's going to talk about what work we have actually done with some of the Ray AI trainers that we actually provide you, so you can actually tune your own particular model using the accelerator libraries, the deep speed with Ray Train. Go for it.
Thank you, Jose. So yes, basically one of Ray and Ray Air's superpowers is that it's extremely flexible. And in essence, Ray allows you to run any Python code you want using any framework and any library while still staying within the Python ecosystem. So you don't have to worry about any YAMLs. You don't have to worry about using new unfamiliar APIs. And by leveraging that flexibility, we have this opinion that there are basically two emerging stacks for open source models. So if you want to train your own model from scratch, then you will use Ray for GPU management and runtime orchestration. Then you will use a high performance training library that, for example, Alpa, which uses JAX. And this is quite similar to what OpenAI has done. So OpenAI is actually using Ray to train their models. On the other side, if you just want to fine-tune pre-trained models, then you don't need all of that complexity and all of that super high performance that you need when you are dealing with large data sizes and long training runs. So fine-tuning is comparatively smaller at scale. It's faster. So you can use libraries that you're familiar with, such as PyTorch, DeepSpeed, and Hugging Face. And you can use Ray to orchestrate and schedule all of that. So under the hood, if we look at the implementation of the transformers trainer in Ray Air, all it really does is it uses PyTorch communication primitives, the PyTorch distributed data parallel or PyTorch FSDP, or any other library that actually uses PyTorch communication, so DeepSpeed, for example, and orchestrates that on an entire Ray cluster. So a Ray cluster can be composed of one node, it can be composed of multiple nodes, it can be running on-prem, it can be running in the cloud, it can be running on Kubernetes. And one really cool thing about it is that by leveraging Ray, you can have multiple different jobs running on a single cluster, and Ray will take care to ensure that all of those jobs have the resources they require without any resource contention or without any conflicts. So you can have several training jobs and a serving job at the same time on a single Ray cluster. Then the Hugging Face trainer that we have, it runs user-defined Hugging Face code without any changes. So you can take any Hugging Face example, any script that they provide, and you can just stick it into a function. You can change maybe 2 or 3 lines of code, return the trainer, and then you pass it to Ray Air Transformers trainer, and it becomes distributed. So you don't have to worry about SSHing into other nodes and you starting scripts there. Ray abstracts all of that, so you can only focus on what really matters, so the actual ML logic. The next thing that we provide is our Ray datasets library, which is a library for distributed datasets. And what that means, it leverages the Ray cluster and the Ray object store to handle datasets that may be too big to fit in memory of a single node. And it also parallelizes pre-processing. And further, you can also create a last-mile data pre-processing with Ray data, and you can use that with Ray Train to do just-in-time data pre-processing. So as the model trains, it gets new batches, and at the same time, the pre-processing pipeline is running. So you don't have to wait for the entire pre-processing to finish. And of course, Ray datasets fully integrates with the Hugging Face dataset. So you can take a dataset from Hugging Face Hub, and you can convert it to a Ray dataset with 1 line of code. We have built-in logging, experiment tracking, and monitoring. So aside from the Ray dashboard, which is our solution to monitor the state of the Ray cluster and the state of various jobs on it, we also integrate with best-in-breed libraries such as MLflow, Comet, OneDB, and also provide an API for you to write your own logging callbacks and monitoring callbacks. And finally, aside from the higher-level transformers trainer, we provide lower-level trainers such as Accelerate Trainer, Lightning Trainer for PyTorch Lightning, and also APIs for you to implement your own trainers if you so desire. So aside from the high-level transformers trainer, we also have an integration with Hugging Face Accelerate. So Hugging Face Accelerate in of itself is like a higher-level API for distributed computing. And it provides a really nice API, but it doesn't actually help you manage those training jobs. So what you can do is you can take a training loop that is written using PyTorch and Hugging Face Accelerate. So you can use the Hugging Face Accelerator abstraction. And you can use all of the functions that it provides, such as deep speed, FSDP, automatic moving of the model to the correct device. And you can distribute that using the Ray AI Accelerate trainer in the same way as you would do with the Transformers API. So you just get your function, and you just pass it to the trainer, and it will automatically be scheduled on the cluster using the scaling config that you provide. Kind of messed that up. And for the PyTorch Lightning, we provide another integration, which works in a very similar way. So you can define your PyTorch Lightning module. Then you provide the Lightning config, which is a Ray AI abstraction, which allows us to basically determine how the module should be run on the cluster. We provide the scaling config, so you can notice the scaling config is a common abstraction between the different trainers that we support. And aside from LLM trainers, we also have scikit-learn trainers, XGBoost trainers, all the best libraries and tools for machine learning. You define the Ray AI Lightning trainer, and then you just need to feed the trainer. And again, Ray is not impacting the ML logic. Ray is not changing how the algorithm works. It doesn't require you to change anything. It just takes care of the scheduling and orchestration and makes sure that your training job runs efficiently and it runs in a distributed manner without you having to worry about that. The clicker has broken. Okay. So if we take a look under the hood on how it actually works, Ray basically spans multiple processes, each of which runs the training loop that you have provided. And by using PyTorch distributed backend, the gradients between the models are synced during distributed data parallel training. But more advanced ways of model parallelism, such as FSDP, deep speed, pipeline parallelism, tensor parallelism are also supported both for training and for inference, but we are focusing on training here. And that basically allows us to completely abstract away the infrastructure. So Ray provides a logical abstraction for the underlying hardware and the underlying cluster. And to you, the developer, the experience is as if you were just running everything on one very large machine, even though it actually is multiple nodes, each with multiple resources. And those machines can also be heterogeneous. So you can have different types of GPUs, you can have different types of nodes, and Ray is able to deal with all of that automatically. So for data ingest, we are using Ray datasets, which is a scalable way to load and pre-process data. It has multiple integrations with different libraries for reading from different data formats. So you can easily read from disk, you can easily read from cloud, from S3, GCP, Spark, Lakehouse, and other such, Snowflake, and other such frameworks. And it's fully distributed. So again, there is this layer of abstraction where the complexities of distributing everything is taken away from you, and you don't have to worry about it. And it can handle data that is too big to fit into one node or even the entire cluster. So for fine-tuning, this might not really be a problem, but if you're, for example, working with vision data or other data types that take up a lot of space, Ray datasets can handle those without requiring you to come up with contrived solutions on how to, for example, load a part of the data from the disk, process it, then save it back to the disk. And one of the features that Ray datasets as a library provides is preprocessors for common ML tasks. So we provide various preprocessors for things like scaling the data, tokenizing the data, labeling the data. But at the core, you can also just write your own Python functions. There is like no special API you have to learn. You basically write a function that uses pandas, and you pass it to the Ray datasets APIs, and that preprocessing function will be executed in a distributed manner automatically on the Ray cluster. And you can create entire pipelines that can be then reused during training and inference. And as I mentioned before, one of the features is streaming. So you can have a preprocessing job that is running concurrently with the training job. So you can have even different preprocessing steps using different types of resources. For example, one of the preprocessing steps might be using a GPU, the other ones might be using CPU, and all of those can feed into a training job that uses multiple GPUs. And all of that is automatically scheduled by Ray. We have different integrations for logging and monitoring, so as I mentioned, we have TensorBoard, MLflow, Comet, 1DB, and all of that, all of the metrics, all of the checkpoints are automatically reported by Ray AI and passed to the respective libraries. And we also provide our own abstraction, the result abstraction. So after training, you can inspect the results. You can see the basic metrics. You can see all the different checkpoints that were saved. So all you need to do is basically just add 1 or 2 lines to the training loop to tell Ray that this should be checkpointed at this moment, and everything else is taken care of. And this sort of checkpointing is very important here because it opens up new possibilities for us. So one of the new features that we have released in Ray 2.5 is distributed checkpointing. So previously, when we were checkpointing in Ray, there was an issue. All of the workers had to send their weights to the head worker, which not only caused a lot of a lot of network traffic, but it also caused memory issues. With Ray 2.5, each of the ranks saves their own part of the checkpoint simultaneously. So if you are using DeepSpeed or FSDP, where each of the ranks has a different checkpoint, then you can automatically save that with Ray Train. And also the resumption of training is fully automatic. So if there is some sort of failure, a node failure perhaps, or if you are using spot instances and the spot instance is preempted, Ray can automatically detect that. It can automatically bring the node back up and automatically resume the training from the latest checkpoint, so you don't have to worry about it. And finally, the checkpoint that is returned after the training can be used for inference and serving. So we provide abstractions that allow you to take the checkpoint and use it with Ray AI predictors and Ray Serve for offline and online inference. So this is the Hugging Face Transformers training workflow that Jules showed before. So yeah, we take the Hugging Face data set, we take the model from the Hugging Face hub, we specify the training arguments, we specify the Hugging Face Transformers trainer, and we call .train. So how would we change this code to run with Ray AI? So first of all, we have to put all of the logic. We have to put all of the logic into a function, and we have to have that function return the Hugging Face trainer object. Then we define the Ray AI Transformers trainer. We pass in that function, we pass in the scaling config, and we specify the Ray data sets that we'll use for training. And even that part is not critical. Like, you are not forced to use Ray data sets. This is best practice, but you can even just define data loading logic inside the function and use that instead if you, for some reason, want to do that. And at the end, all you need to do is call trainer.fit. So just to summarize, in order to distribute a Hugging Face training workload, you basically just need 3 steps. First, you can use Ray datasets for ingest. Second, you just need to use the existing Hugging Face code. So again, like any example that is on the Hugging Face repository or documentation can be modified to run with Ray AI using those very simple steps. And finally, you get the benefits of integrating with the rest of the Ray AI ecosystem. So the other libraries that we provide in Ray AI, aside from the training and datasets libraries, is RayTune. So this might not be as important for LLMs, but if you are, for example, doing time series analysis or tabular data analysis, you may need to run hyperparameter sweeps. And in order to run hyperparameter sweeps effectively, you will most likely need a lot of trials, a lot of configurations to search through the search space. And RayTune can automatically do that. So you can pass one of the trainers that we have into the tuner abstraction and call tuner.fit. And you can actually distribute distributed training jobs. So you can have nested parallelism, which is automatically managed by Ray. And after you have your model, you'll probably want to use it. So you'll want to do inference on it. So you can do batch inference, offline inference, and for that you can still use Ray datasets. So Ray datasets actually allows you to use the checkpoint that you have trained with our batch predictor abstraction, and it can take in a very large data set, and it can automatically parallelize inference on that data set in an optimal manner. Or for online inference, if you want to serve network traffic, you can use Ray Serve, which is our distributed serving library, which also has many cool features, such as auto-scaling, integration with fast API, and more. And you can create a Ray Serve deployment using the checkpoint that you have obtained from a Ray Air trainer. So for the batch predictor, we have a Hugging Face predictor abstraction, which uses Hugging Face pipelines under the hood. So we are not changing the logic again, like we are just parallelizing it, and it doesn't require you to learn any new concepts or modify your code. And you can get a Ray data set, and you can pass it to the predictor, and it will automatically be parallelized. So just to briefly touch upon serving large language models with Ray Serve. So Ray Serve is a part of Ray Air for serving models for online inference, also offline inference, but the main idea is online inference. And it actually powers one of the projects that we are working on, which is called Aviary, which is our open source solution for serving multiple large language models in an optimized fashion. So Ray Serve is scalable. It can automatically scale up and down in response to the demand. It is low latency, it is efficient, it is fault tolerant. So if, for example, you're using spot nodes to serve your models, they go down, Ray Serve can automatically bring them back up. It has first-class support for multimodal inference. It is fully Pythonic. You don't need to get out of the Python ecosystem or your Python scripts for any moment. And you can mix business logic and machine learning. So you can actually have a Ray Serve deployment pipeline for different steps, such as generating embeddings, getting the inference from the model, and so on. And all of those steps can auto-scale independently. So the project that we are talking about, Aviary, is actually powered by Ray Serve. You can access it right now. It is an open source project that we also provide a hosted version for. And it serves multiple open source models that up to 40 billion parameters and allow you to easily compare the outputs from the different models. And you can also deploy it yourself. And we have many exciting news planned for Aviary, so stay tuned in regards to that. So now we have a short demo, so hopefully this will work because it's a live demo. So what we want to showcase is what we have been talking about all this time. So we want to take an open source model, the GPTJ model, which has been trained on a large data set. We want to get it from the Hugging Face Hub, and we want to fine tune it on a Shakespeare data set to hopefully give it a bit more of a Shakespearean flow. And let me see. Okay, hope this didn't terminate yet. Okay, so this is Anyscale. So I'll be running this on Anyscale, which is our managed Ray solution. But all of the code that you will see here is not only publicly available in our documentation, but you can run it on any hardware using Ray open source without any changes. So we can see that we have a cluster of multiple nodes here. So we have 32 nodes. Each of the nodes has a single GPU. And this is the Ray dashboard, by the way, which allows you to monitor the health of the cluster. So we have a notebook here. We'll just run through it real quick. So first, we are going to set up Ray. We are going to define some parameters. You can see 32 workers. We will be using GPU. We are going to initialize Ray. So one cool feature of Ray is those runtime environments. So you can have Ray tasks and actors automatically run in like a PIP environment, and you can have different actors run in different environments. So you can, for example, serve one model using this version of the library and serve another using a different version of the library. This is just some model downloading code, which hopefully shouldn't take too long. We'll be getting the tiny Shakespeare dataset from Hugging Face Hub. So this is a very small dataset. This is a toy example, of course, but
we are constrained by time. So we create a Ray data set from the Hugging Face data set. As you can see, we have full integration. All you need to do is call from Hugging Face. And now this Hugging Face data set becomes a Ray data set, and it can be used with Ray AI. We define some more pre-processing code. So we obviously have to tokenize the data set. We have to split the data set into batches. And all of this pre-processing is actually going to be parallelized with Ray AI. And this is the training function that we are using. So we are using DeepSpeed. DeepSpeed is a library that allows you to efficiently train the models, especially if you are constrained by memory. And as you can see, we specify the DeepSpeed configuration. And we just pass it to the Hugging Face transformers training arguments. And then we load the model, we load the tokenizer, and we initialize the Hugging Face trainer. And obviously, you can do the same thing with pure PyTorch. You can do the same thing with Accelerate, with PyTorch Lightning, all of the different integrations that we provide. We initialize the Ray AI transformers trainer, and we start the training. So I've set the number of steps in the training to 5. So hopefully this finishes quickly. Obviously, this is not a full training run, so I don't expect the model to work very well. But still, you can see we get the log outputs, we get the status of the job, and we can also monitor the Ray cluster to see the resource utilization, what sort of Ray tasks are being run. So we can see the inner train loop is scheduled here. So this is unfortunately going to take a while because the model has to be downloaded, the model has to be loaded, it has to be trained, but I can show the other parts of the notebook later. So after we are done with training, we get the checkpoint object from the result, and checkpoint is a Ray AI abstraction. It's basically a wrapper for any data you want, but if you create a checkpoint from a model, then we can actually use that checkpoint for inference later. And we can create a transformers predictor, a Ray AI transformers predictor from that checkpoint, set the arguments that will be used by the underlying Hugging Face pipeline inside of it, and call predict on the prompt's data frame. And that will automatically run with our fine-tuned model. So while this is chugging on, actually we can see that now that it has started training, so we can see the GPU utilization, we can see the memory utilized. We can also look at metrics, so Ray Dashboard integrates with Grafana, and we can see the GPU utilization over time. So over time, we are a little bit over time, so we also have a recording. So this recording will hopefully show you
the prediction.
How to do the prediction after the training has completed.
Just move down.
Yeah. So we get the checkpoint. You can see it refers to this local path. It can also refer to a cloud path or an NSF path. We set the preprocessor to none so that we can use the Hugging Face pipeline, and we create the predictor, and we can see what sort of sentences the model will generate. So this is obviously not a model fine-tuned for question answering. This is not a model fine-tuned for chatting. It's just a base model. We have run a few steps of fine-tuning. But we can already see that even just with a few steps, it's kind of starting to get that Shakespearean vibe. It's not a good model yet, but with some more time and with some more compute, so you can use Ray to effortlessly scale up and down depending on what is your budget and what is the compute you have access to, we would be able to make this a pretty good model.
I think we're out of time. We didn't mean to filibuster you guys, but there's not another talk after this, so we're going to hang around if you actually have any questions. If you want to try this notebook, you can scan this. It's available on our docs. All the code is there. As I said, you will actually can run this on a cluster that has GPU and CPU as well. So what we essentially showed you, you can actually do a fine-tuned model, taking a Hugging Face, using the Ray AI transformers, libraries that we have, and you can actually run that in a distributed manner. What you saw over here, we had 32 nodes, we had 32 GPUs, we were doing both CPUs and GPU utilization. You could actually use the dashboard to see in real time how the training and everything is progressing. And once that's done, we loaded the model on the checkpoint and we did the inference. So that was in a completely end-to-end, from data ingestion all the way to inference serving using Ray AI with the libraries available. And that was the scenario 3 that I was talking about. So any questions? Fire away. Yeah.
Yeah, so cool stuff. It's my first time seeing
Thank you.
Ray. Very exciting. So question sort of as a startup, I have my Kubernetes cluster. We have subscription for Databricks. How would I get my hands on this? Like everything is great and easy once it's set up, but there's nobody, helicoptering in and doing all this for me. So I need to get through this initial pain. How would you recommend I do that?
Well, I mean, yesterday, I don't know if you were attended to a particular talk. There was a joint effort between Databricks and Anyscale to provide the ability to running Ray on Spark. Ray on Spark, right? And so what you do is you actually use your existing Spark cluster and you create Ray nodes on it. And then once the Ray nodes are created, a Ray cluster is created, depending on how many executors that you have, you can use now Ray library natively to talk to the Ray cluster, right? So in the case of Kubernetes, you would, if you're using Databricks on GCP, then you would actually just use your Ray cluster, your Spark cluster to create your Ray cluster and then talk directly to it. There's a bit of limitations over there because, as Anthony pointed out, we actually saw that this particular training model was using a heterogeneous cluster that was using CPUs and GPUs. Spark is a homogeneous cluster. So if you were doing deep learning training, or if you were doing deep learning inference, then you won't be able to do that. You would actually have a separate cluster.
So is there a way to set this up? I mean, by Kubernetes cluster, I have a completely separate Kubernetes cluster in AWS. So how would it?
Yeah. So for Kubernetes, Kubernetes is supported as a first-class citizen in Ray. There is the KubeRay project that we maintain, and it basically provides a Ray operator for your Kubernetes cluster. And it allows you to very easily set up a Ray cluster on Kubernetes. And you can also, if you so choose, you can also use the EC2 instances directly without having to go through Kubernetes, which is also fully supported.
So as I pointed out, if you didn't want to use Spark on Ray, this would be the option that allows you the full functionality of Array, right? So you create your Kubernetes, you create your Array cluster on Kubernetes, and then from your Databricks notebook, you just connect it using your URL on the head node, and now you're talking to your Kubernetes cluster.
I guess you can just do it on AWS directly.
Yes.
And the second question, sorry if there's other people as well, was looking forward, I quickly looked at your website before the talk and it said, AIR is currently in beta, and I was wondering, what does that mean in terms of the future of the project? Is it going to be an open source project? What is, in terms of features, beta, and what is kind of the monetization for the company? Are you guys looking to make a service, or is it going to be, because, if I get into this and spend a lot of effort, God forbid, move a portion of Cisco into it, then.
So I can answer the first part of the question. So everything we showed you today is available now. It's all fully open source. All the code that we have run here, it's open source. We have no plans of making any of this proprietary. It's in beta because we are still trying to stabilize the APIs, but we are pretty close to that. And there are definitely going to be more features. There are going to be more optimizations, but all of that is going to remain free and open source.
Yeah, so if you just do Ray install all, you will actually get Ray AI, right, directly. And in a couple of months, if and when that's more stabilized, when we do a GA, it's going to be available both on open source, and there might be an optimized version available on Anyscale.
So in terms of monetization, so what we provide is we provide the Anyscale managed Ray service. So this is basically like a layer on top of your cloud provider that allows you to very easily configure and run and launch multiple Ray clusters. But it's basically like a very simple way for you to take care of the MLOps problem. We just take care of it for you. And we also provide some under-the-hood optimizations, not necessarily for Ray, but for example, for the time it takes for a node to start up, the instance provisioning, and optimized auto-scaling. So those are all things that can save you time and money.
In short, if you're a startup company, you don't want to deal with managing the open source cluster because you would have to, right? One of the things I talked about earlier was one of the pain points of the infrastructure management is you have to do it yourself. But if you actually use the AnyScale, that burden is taken away from you. And as Anthony pointed out, you just focus on what you actually have to build using the toolkits available. Yeah.
Apologies if you've run over this before, but is there like a way I can just like test array like on a single machine, like local?
Yeah, you can do it. So array cluster can be composed of one node, and all you need to do for that is in Python import ray init. You have array cluster. That's all you need. And the code that you write is going to run in the same way no matter how big the cluster is. Obviously, if it requires resources you don't have, it's not going to run, but like the syntax and the logic and everything is going to stay the same. So you can actually develop on your laptop and use the same code that you've been developing on a cluster that is composed of multiple nodes.
And then like I would just have to put in the parameters or whatever to move it to prod.
Yeah, exactly. Like you would scale it up basically.
So try it, pip install on your laptop tonight. It'll keep you awake.
It even works on Google Colab. It doesn't work that well because
I know. Well, it might be occur to you insomnia. Oh, this is working. I'm going to go to sleep. Any other question? Yeah, go ahead. So I think the Ray on Spark on Databricks is still sort of experimental, right? All the operational stuff that Databricks manages, they might actually have to do that if they actually want to do the Ray cluster. I can't speak for that side of the things, but I can speak for the AnyScale side of things, because if you wanted all the functionality of Ray that gives you, then the AnyScale will take care of all the management, right? It provides you the development. What you actually saw Anthony showing you was a notebook, or you can actually use Visual Studio. So as if you're actually developing your laptop, or you're actually doing it on a staging environment, and then you can move that code over to production. I hope I answered that question, because I'm not trying to equivocate over here, but yeah, go ahead.
So I would just add, so we have multiple users that are using just open source Ray, and for example, Spotify has built an entire ML platform for data scientists. So they have multiple Ray clusters, and their data scientists just connect to those Ray clusters, and they run their jobs on top of that. So it simplifies life for the data scientists, because they don't have to really worry too much about writing distributed code, because Ray abstracts that. And it also simplifies life for the management side of things, because first of all, Ray code is going to run the same no matter the cloud provider, no matter the hardware. So you are not locked into a specific vendor, you are not locked into a specific region. All of that is basically abstracted, and with the monitoring tools that we provide, it's very easy to see if something's going wrong, if you are lacking resources and things like that. Yeah, so there are like two ways, right? So you can either have start a Ray cluster for a specific job, or other users, what they prefer is they just have like large Ray clusters that are shared between multiple jobs. So there is like no best way. So if you have like single tenancy, then you have more stronger guarantees on consistency. And like if something goes wrong, then only this job dies. But if you have a large Ray cluster, which is actually pretty stable, you can then make best use of the available resources using Ray scheduling and Ray autoscaling, and make sure that, for example, one of the very cool use cases we've heard about from one of our users is that they have a serving job, and they also have a training job at the same time. So when there is not much demand for serving, they scale up the training job, and when there is large demand for serving, they can automatically scale down the training job to free up resources for the serving. Yeah, so for that, so yeah, Ray basically just, you can think it's selling it short, but basically you can think of Ray as just starting processes. And what happens in those processes is entirely up to you. So in the example that we used, using PyTorch distributed communication, this is still using Nikhil. This is still using all the best-in-breed communication backends. But Ray makes sure that all the processes are running correctly, they are using the correct resources, and you don't have to worry about all the headache of managing a very large training job.
Yeah, once the trainer creates the Python process groups, we just wait for it to actually finish. And we don't interfere, we don't try to change the protocol. As Anthony pointed out, it's just an orchestration of saying, I'm using DDP, create the process group using PyTorch libraries, and boom, it just goes. And all the communication happens behind the scenes. So we don't try to write a one protocol. Why would you do that, right?
Yeah, so we have actually fixed that in the latest release. So there has been a D-Suite update which kind of messed things up. So we have released Ray 2.5 very recently. I think if you run it with that, it should be working fine.
I think those guys are giving us a signal that we should probably end, but we're going to hang around, right? But thanks a lot for coming. And
yeah, we actually have a booth in the expo hall. So if you would like to swing by and talk to us.
Come by, but swing by if you have any further questions. But yeah, we'll hang around here.
Yeah.
Thank you.